Hi everyone, today we're going to be talking about derivative formulas. In this section, we will learn some rules and formulas for derivatives so we don't have to take that tedious limit every time. Before we learn these formulas, let's talk about some derivative notation. Typically, we use the prime notation to denote a derivative, that is f prime of x. Sometimes we will drop the parentheses x portion and just write f prime. We can also use the following notations shown below. So we have f prime of x, which is equal or the same thing as y prime, which is the same thing as df over dx, which is the same thing as dy over dx, which is the same thing as d over dx of f of x, which is equal to d over dx of y. We also need a notation for evaluating derivatives when using the fractional notation. So if we want to evaluate the derivative at x equals a, all of the following are equivalent. So we have f prime of a, which is the same thing as y prime with this vertical bar next to it, evaluated at x equals a, like that, which is the same thing as df over dx with this vertical bar, evaluated at x equals a like that, which is the same thing as dy over dx with the vertical bar evaluated at x equals a like that. Let's talk about the constant rule. So let c be a constant, then f of x equals c is known as a constant function and its derivative is always 0. So f prime of x, or d over dx of this constant function is equal to 0. And the reason that is because if you have a constant function like this, if you take the slope of the tangent line anywhere, the slope of the tangent line is always going to be 0 because it's a horizontal line. And recall from algebra that the slope of a horizontal line is 0. Okay, so now we can talk about the power rule. The power rule says if you have a function f of x which is equal to x to the power of n, where n is some real number, then the derivative f prime of x is equal to n times x to the n minus 1 power. Let's show why that is. So if you have f prime of x, that's going to equal, remember from a previous section, that's equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And in this case, if you were to plug in x plus h into the function, then that's equal to the limit as h goes to 0 of x plus h to the nth power minus x to the n all over h. Now, n is some real number, and we need to expand this thing here. And we don't know what n is, we just know that it's some real number. So the way that we expand that polynomial is it ends up looking something like this. So we have the limit as h goes to 0 of, now it's going to look kind of ugly, but we have x to the nth power plus n times x to the n minus 1 times h plus n times n minus 1 over 1 times 2 times x to the n minus 2 times h squared plus dot 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 plus h to the nth power. So it's this really long polynomial depending on what n is, and then we're going to subtract off x to the nth, and that is all over h. Now, what's going to end up happening is, notice that this x to the n will subtract with this x to the n, and then all of these terms have an h in them. So we're going to factor out the h, and it's going to divide with the h in the denominator. So after we do all of that, then we get that the limit as h approaches 0 of nx to the n minus 1 plus n times n minus 1 over 1 times 2 x to the n minus 2 h plus dot 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 plus h to the n minus 1. And now, because this is a polynomial, we can substitute in h equaling 0. And notice that every term except the first term has an h. And so what this is going to leave us with is, after we've plugged in 0, the only thing left is this term right here. So what we're left with is n times x to the n minus 1 power. And that was basically a proof of the power rule. And in math, whenever you finish a proof, you have some kind of symbol to indicate that you are done with your proof. Oftentimes you'll see a square, a shaded in square. When I took calculus, my teacher would use this symbol to indicate that she was done with her proof. So that is the proof of the power rule. And it seems kind of complicated, but in practice, this makes life a lot easier for us. Instead of having to calculate the limit definition of a derivative, we can use the power rule. Example 1 wants us to find the derivative of the following functions, and we can use the rules that we have learned above. So f of x equals -9. -9 is a constant function, so by using the constant rule, we can just say that f prime of x is equal to 0 because f of x is a constant function. Okay, so this one, if we do f prime of x, we'll use the power rule. So remember, it's n times x to the power of n minus 1. So here n is 4. So we'd do 4 times x, and then we'd raise it to a power of 1 less than the original power, which is 3. Okay, so f of x is equal to the square root of x in example C. The first thing that I would do is rewrite this as a fractional exponent. So if you remember from algebra, this is the same thing as x to the 1/2 power. Now we have an exponent and we can use the power rule. So that's going to imply that f prime of x is equal to, I'm going to bring the power down, so I have 1/2 x, and then 1/2 minus 1 is -1/2. And sometimes you'll see this rewritten as 1/2 times 1 over the square root of x. Those are equivalent, and then you can rewrite that as 1 over 2 root x. So I'm okay with this version or this version, either is fine. And this was again using the power rule. Okay. Example D, we have f of x is equal to 1 over x cubed. I'm going to rewrite that as x to the -3rd power. And then that's going to imply that f prime of x is equal to, I'm going to bring the power down, so I have -3 x, and then decrease that number by 1. So -3 minus 1 is -4. So you could write your derivative like that, or like -3 over x to the 4th power. Either of those are fine. I forgot to box my previous answers, so let me go back and do that. All right, so E, we have f of x equals x to the power of 1.7, so that means that f prime of x is equal to 1.7x, and then I will decrease the power by 1, so that leaves us with 0.7. So that is our derivative function for part E.